All right, so we're going to take a look at a uniprocessor solution to this Monte Carlo pi estimation problem. We're basically a very straightforward program here. We're going to go ahead and create a random number generator on this line of the code, and then a distribution based on that random number generator that'll give me random long doubles. So this, could be pretty sizable. I'm not sure. I'll have to check in between videos here as to the size of that, but that's at least 64-bit doubles. It could be longer, but they'll produce random numbers between 0 and 1. Okay. Int numin, that'll be what we use to count the number of things that we have inside our circle. And then these are just temporary variables for the x and y coordinate of the dart that we throw and the distance that is from the center. So I'm going to throw 100 million darts using this for loop. We just calculate the x, y coordinate of the dart, calculate our distance, and remember we set things up nicely so that I don't have to do square roots, I don't have to do any subtraction, I just square each point. And then I check to see if that distance is less than or equal to 1, which would make that point within the circle. If it is, I'll increment numin by 1. So do that 100 million times, and then at the end, I'll see out the total that were in the circle divided by 100 million, that result times 4, and that should be my estimate of the value of pi. So my makefile looks pretty similar to the ones that we were using in the MPI section. The part that we're looking at right now is this line right here. We're just compiling this using the standard C++ options and writing out the result to a subdirectory called bin / and then our file name will be uini-pi. So make my directory, make my program. Okay, the HTC part, which we're going to run on the cluster, is also there, so we'll take a look at that later. But if I want to execute this, it's just in the bin directory, the uni-mpi or uni-pi program. Run that, it'll do its 100 million darts. And there's my estimate, 31416, which is not bad, 314159, and so on would be the real value. Try it again, and it should differ slightly, and it does because randomness. Okay, now let's take a look at the HTC one of these. So it'll be very similar. And what we're going to do with this is actually run it as an MPI process on the cluster. So we're not using Boink or Condor. We're just using our own resources as a HTC resource instead of an HPC resource. But this will start out very similar to how we normally would an MPI program. We initialize the arguments, or initialize the MPI system, grab my rank and the size of the communicator. And then from there on out, notice that I don't have any different pieces here for a root and the subprocesses. I'm going to be doing, everyone's going to be doing exactly the same thing. So one of the things I have to do in order for this to work is I have to add a value to the random number seed. So I'll add my rank, processor rank, to the random number generator seed. Otherwise, they would all have exactly the same seed, presuming that they all start at the same millisecond. And if that's the situation, they're all going to produce exactly the same results, which is not what I want. So seed the generator with the processor's rank. From then on out, this is all the same as it was. And now what we'll do, instead of outputting our estimate, I'm going to output a hashtag, a space, and then the number that we're in the circle. And that way I'll collect all those numbers back with a script, take those numbers, add them together, and get my overall estimate for pi. So my script here that's going to do this will just take the output file that the MPI processes create, read all of the lines in that output file. If that line happens to be prefixed with the hashtag, so that way I can tell my output apart from the output of the Slurm system or the MPI system, then I will just grab everything in that line except the hashtag, turn it into a number, add it to my sum, add 100 million to the number of points that I've thrown, because each one of the processes is doing that many darts, and then at the end divide that the sum by the number, multiply by 4, and that's my output. So if I run this on my local system with 8 processes, HTC Pi, there we go. I'm going to not redirect the output yet. Allow access, and after they're all done, there's the 8 pieces. Now if I run it again and redirect that output to a file, it'll save all that output there. So now if I look at that, see why I want to have a hashtag, a special marker on these, so I can tell them apart from all this junk up here that's not part of my output. And now I can feed that into my script that does the processing. And there we go, 314159. That's a pretty good estimate. We could also run this on our cluster system with a Slurm job. So I'm going to pause the video for a second and then we'll do that. All right, now I'm logged on to the supercomputer here. I'm in the directory that contains all that, those programs that I just looked at. Make sure that they're all up to date here. And I do have a Slurm job file. This will run it on 100 cores, output to this pi-whatever.out, and then just executes that program. So let's go ahead and run that. It's executed, and we'll wait a little bit till I get my output back. And let's see if there we go. So let's go ahead. I can now process that. Make sure that this is actually the complete version. Yeah, that file hasn't changed. So load my Python module, and then I can cap my output file into that process program. And there we go. There's my output. My estimate is 314157. So again, not too bad. There we go. So that's using our cluster sort of to simulate an HTC system.